Good morning, everyone. We are going to talk about Investigation 2 today, and I just want to talk you through the lab from start to finish so that you have an idea of what's going on and you have all the information you need before you start the lab. So in Investigation 2, our goal is to figure out how much copper is in a shell casing. So let me show you what our shell casing is. So basically we've taken a shotgun shell, which is made out of brass. And so brass is going to be an alloy, a mixture of copper and zinc together. And we've sawed off part of it just to make it a more manageable size. So here we go. This is going to be our little casing piece to analyze. And what we want to figure out is what percentage of copper is in our mixture. So what is the mass percent of copper in our little sample? And we're going to use our spectrophotometer to do this. So in order to use a spectrophotometer to analyze the amount of an ion in a solution, we need the whole sample to be dissolved. So we're going to dissolve the shell casing, and then we're going to use a spectrophotometer to analyze how much copper is in the sample. So before we get to this point, one of the first things we need to do is we need to figure out which wavelength we're going to set our spectrophotometer to do in order to analyze copper. Now, in Investigation 1, we used blue food dye, and we set our spectrophotometer to 630 nanometers because at 630 nanometers, blue food dye absorbs light at 630 nanometers very well. And you can see a spectrum for red food coloring here in front of us. And you can see what they've done is they've taken red food coloring and they just took one concentration of red food coloring the whole way through this graph, and they measured the absorbance at, what is this, maybe 350, and then maybe 375, and 400, and 425, and 450, and 475, and 500. And so they just kept the sample in their spectrophotometer and changed the wavelength. And every time they changed the wavelength, they took a new absorption reading. And from those wavelengths that they were changing and the absorption, which changed as a result, they made this spectrum, they made this graph for red food coloring. So you can see that the absorbance of red food coloring is not going to be the same at every single wavelength. You can see when the spectrophotometer is set to block all the wavelengths except for 500 nanometers, the absorbance is right above 0.4. When the spectrophotometer is set to block all light wavelengths except for 600, the absorbance is much, much lower, maybe 0.01, 0.02 absorbance. And so as your wavelength changes, as you change which wavelength is getting through the spectrophotometer and going through your sample and hitting the detector, the molecules in your sample are going to measure or absorb. They're going to absorb those wavelengths differently. So we need to figure out what the wavelength is for copper that's going to be absorbed really well. We don't want to choose a wavelength for copper that is going to absorb minimally. Like if we chose 600 to analyze red food coloring, we're going to get super low absorbances and maybe absorbances that are too low for our spectrophotometer to actually like detect well. So there's a couple considerations that you need to make when you are analyzing a graph like this. Okay, so we're going to make a graph like this for copper so that we can pick a wavelength. And when you are looking at a graph like this, you want to pick an absorbance that is preferably below 1.0 or maybe 1.2. When you get up this high in absorbance, what happens is your sample is absorbing a lot of the light, and not very much light is getting through and actually hitting your detector. And so the cheaper your instrument is, the more error your detector is going to have. It's not going to be as good of a detector. Now, our spectrophotometer is wonderful and I love it, but it's not the most expensive spectrophotometer in the world. It's a spectrophotometer that a high school can afford, right? And so our detector is not going to be the most sensitive thing in the world. So what we want to do is we want to make sure enough light is hitting our detector that our detector can actually accurately pick up and read the light that's hitting it. So when we pick an absorbance, we usually want to stay below 1.0. If you're working with a better spectrophotometer, you can probably push that limit to about 1.2. Okay, consideration number 2 is the peaks on your graph. If you have a peak that's really sharp or you have a peak that's incomplete, you don't want to pick the max absorbance from those peaks. You want to pick the max absorbance from a peak that is the tallest peak you have that is still also broad. So this peak in the middle here is a very broad peak. It doesn't come to a sharp peak at the top. It's complete. It goes up, it goes down. And so we're going to pick one of the highest points off of this curve on our graph. So your highest peak would be about here, and that would be maybe 540 would be a good wavelength. But honestly, if you picked any wavelength in this general region, you would get a pretty good reading out of it. So here's the next thing you are going to do. This is another example of multiple copper compounds, and we'll come back to this one in just a second. You are going to create a graph. So you need to go watch the video in order to collect data for our pre-lab in order to create this graph. So what I've done is I've put a copper sample into our spectrophotometer. It's our 0.4 stock, 0.4 molarity sample of copper nitrate. And I've started at a wavelength of 400, and then I've changed the wavelength every 20 nanometers all the way up to 700 or maybe a little bit above. So I want you to create a graph of the absorbance versus wavelength for this data. So watch the video, collect the data, and then you're going to create a graph. Now, in class, what we'll do is we'll have, once you guys bring in your graphs, we'll have a discussion as to which wavelength we can pick off of that graph to have a good absorbance of copper. The other thing I want to talk about in class is how we know that copper is doing the absorbance and not the anion with copper. And that's what this graph has to do with. So we'll come back to this graph when we have that discussion. All right, the other thing I need you to do in this pre-lab is to calculate the amount of nitric acid we need. So like I said, we have our little brass sample here that we're going to dissolve, and we need to dissolve it because we can't put a solid into the spectrophotometer. If we put a solid into the spectrophotometer, then the solid is going to reflect all the light, absorb maybe some of it, and transmit none of the light. And so our spectrophotometer can't read that, because what our spec reads is the amount of light that is transmitted. So a solid's not going to transmit any light. We can't put a solid in there. So we have to dissolve our sample, and we're going to dissolve our brass sample in nitric acid. You can see the reaction for that down here at the bottom. And our sample, our little brass sample, is going to weigh 1.300 grams. And so what I need you to do is I need you to calculate the amount of nitric acid in milliliters that we're going to need to completely dissolve our sample. So for simplicity's sake, we're going to assume that our sample is 100% copper. So you can just take the mass, assuming that's all copper, and convert it into nitric acid that we're going to need. The stock solution of our nitric acid that we have is 15.9 molar. Okay, last thing I need you to do for the pre-lab for this lab is I need you to calculate some concentrations for me so that we can make a couple solutions. So the next part of this lab is we're going to be actually collecting absorbance for an unknown sample, which is our little brass sample. So we're going to collect it, but that's an unknown concentration. The concentration is what we're trying to figure out. So that is our unknown. So in order to figure out what that concentration is from absorbance, we need a graph that relates absorbance to concentration. And so this is going to be a standard graph. It's a graph that we create off of knowns so that we have a relationship between absorbance and concentration that we can compare our unknown to. So we're going to make this graph off of our knowns. And our knowns are going to be 0.4 molarity of copper nitrate. That's our stock. Then we're going to create a 0.2 molarity, a 0.1 molarity, a 0.05 molarity, and a 0.025 molarity concentration for solutions. So we're going to have 5 different solutions at 5 different concentrations. We'll put them all in the spectrophotometer, and we'll make a graph that relates these concentrations. 0.4, I guess that might be, I don't know which way we'll do it. 0.4, 0.2, 0.1, 0.05, 0.25, okay? And then we'll take the absorbance for all of these, and we'll get a little relationship between concentration and absorbance. So then what we can do is we can take our unknown concentration, take an absorbance reading, go over to the graph, and then down to what the concentration is. So we are going to create these solutions, and we need to figure out, we know what their concentrations will be, but we need to figure out how much of the stock solution we need to take out and dilute with water in order to create our solution B. Now, we're going to do this dilution a little bit differently than we did the dilutions on investigation 1 for 2 reasons. First of all, when we get down to this molarity, way down on E, that's a very small molarity. And so if we started with our stock solution and we pulled some out and mixed it with water to make our solution E at 0.0250 molar, it'd be such a small amount that we would struggle to measure it well. We would need probably a specialized pipette or a pipetter in order to take out the stock accurately and mix it with water for E. So that's problem number one. Problem number two is if we take all these straight from our stock solution, we're going to eventually run out of our stock solution pretty quickly. So we don't want to do that either. We don't want to waste our stock solution. So what we're going to do is we are going to do this through what's called a serial dilution. So let me tell you about a serial dilution real fast. All right. In our serial dilution process, what we're going to do is we're going to take an amount. Here's our stock solution at 10 mils. It's going to be 0.4 molar copper nitrate. And what we want to create is 10 mils of a 0.2 molar solution. So the first question we need to ask ourselves is, how many moles? How many moles of copper nitrate is going to be in the solution that we want? So in order to figure this out, you take the concentration, moles per liter, and you multiply it by the volume. So we're going to get 0.002 moles. Okay, I want 0.002 moles to end up in my new solution. And this is solution B. If our stock solution is A, then this is going to be solution B. Okay, so the next question we need to be asking ourselves is, how much volume of the stock contains this amount of moles? So I know I want 0.002 moles. So what volume of the stock contains this so that I can take that volume of the stock, transfer it into my new container, and then dilute to the top with water. Okay, so we'll start with our moles here, 0.002 moles, and we're going to multiply it. We want moles on the bottom and liters on the top. And this, I want to know the volume of stock, so I'm going to use my molarity of stock here. Okay, so this is going to equal 0.005 liters of our stock. Okay, now notice that all the way through this calculation, my volumes agree. So in the beginning, I used molarity of B and volume of B, and I got the moles that's going to be contained in solution B. Now that same moles that is going to be contained in solution B is also going to be taken out of solution A. And then I multiplied that by the molarity of A, and then I got the volume of A that I'm going to need to take out. So notice how my molarity and my volume and my moles all agree with what they are referring to. Okay, so this is the process for a serial dilution. Now on the next one, we're going to want another solution. We'll call it solution C. And what we want here is we want 10 milliliters in 0.1 molar. And so for this, you're going to go through the exact same process. Okay, how many moles is this going to contain? And then how much volume of B am I going to take out to get that amount of moles in C? You put that amount of moles at the bottom, and then you fill it with water to 10 milliliters. So this is called a serial dilution. It's a serial dilution because we're going from A to B and then B to C. In a normal dilution, what we would do is we would go from stock to create B, then from stock to create C, then from stock to create D. But like I said before, if we did that, by the time you got to taking the amount of the stock out and putting it into solution E, that amount you take out of the stock is too small to accurately measure. Whereas if we go in a serial dilution, the amount that we take out of the previous solution is always going to be a measurable amount. Also, I'm not continually drawing out of my stock to make these. I'm going to draw out of the one before it. So I actually only use my stock solution once. So in that way, I conserve my stock solution. I'm not going to use it unnecessarily, and I'm not going to run out of it as soon. A couple notes on dilution. So I'm going to erase what's up here. And I want to talk you through a couple notes on dilution. So when you take, so this, let's pretend this is our stock solution. And we're going to take out of our stock solution to create our solution B. Okay, so what we take out, we're going to put that into our new container, and I think it was 0.005 liters. So let's just put that in there. Okay, so one note in dilution, you want to put in your stock solution first. That's the first thing you do. And then after you have that in there, then you add in water up until the mark that you want. So that water is going to be the second thing you add. And again, we are not measuring out the stock solution and the water separately. We're going to measure out the stock solution, and then we're going to add water up to our mark, because water solutions are not always additive. Okay, if you add 100 milliliters of nitric acid to 100 milliliters of sodium hydroxide, you're not going to get 200 milliliters. In this case, 1 plus 1 does not always equal 2. Sometimes the solutions fit in between each other. And so if you add 100 mils and 100 mils, you actually get, like, let's say 190 milliliters, because the solutions are fitting into each other. So every time you do a dilution, you're going to dilute up to the mark you want. You're not going to measure out the water and the stock solution separately and mix them, because you might not end up with the amount that you want to end up with. Second of all, if you are measuring in a graduated cylinder, you can do this in a graduated cylinder, especially because we don't have any volumetric flasks that are 10 milliliter volumetric flasks. And so we need to use another piece of glassware. So you can do this in a graduated cylinder. Let's say you add in your stock solution first. And then after your stock solution is in there, you're going to add water up until the 10 milliliter mark. You can do it in a graduated cylinder, but don't forget, graduated cylinders are really, really, really bad at mixing things. So you're probably going to have to pour this out into an Erlenmeyer flask. in order to swirl it around, or possibly into a beaker, which are also decent mixing devices. And then you're going to have to pour it back into your graduated cylinder to make sure you have actually hit that 10 milliliter mark. You're going to introduce more air by doing it this way. You could also put a glove on, cap your graduated cylinder, and shake it, and then go back and add water as you need to the 10 milliliter mark. But just be warned, graduated cylinders are really bad mixing devices. So if you are doing this in a graduated cylinder, you have to take a couple steps to make sure that the solutions actually mix together, and then that you actually did dilute to that 10 milliliter mark. Okay, just a couple more things. I want to just walk you through the whole lab so you know what you're doing. After we make these dilutions, I'll create a video so that you can see the absorbance values for each of the samples, A through E. You're going to use these values and their relative concentrations, and you are going to create yourself your standard graph. You want to make it a scatter plot. You want to include a line of best fit, and you also want to include an equation for your line of best fit. After we create that graph, we are going to test our unknown. So we'll put our dissolved brass sample into the spectrophotometer, take an absorbance reading, and then we will use that absorbance reading to figure out what the concentration is. And that will be the whole lab. All right, so just to recap, that was a lot of information. I just kind of want to recap what you need to do for the pre-lab. So you need to watch the video where we collect data for copper nitrate at the different wavelengths between 400 nanometers and 700 nanometers, and you need to create a graph that we can use in order to choose a wavelength. I also need you to calculate the amount of nitric acid we're going to need to completely dissolve our brass sample. And lastly, I need you to do the dilution calculations and figure out what volume do I need from A to create B, and what volume do I need from B to create C, what volume do I need from C to create D, and what volume do I need from D to create E. So you're going to do 4 different calculations to figure out the volume I need in every step of our serial dilution. All right, send me questions. So glad you're still with me. Let me know how it goes. We'll talk in class.